block all these colors, let's say with a filter, and we're going to get blue. We can block all the blue and the green and the yellow, and we're going to get this orange-red. Sometimes light hits something, and what gets reflected to you is only part of the spectrum. That's why things are colored. What we see is when light hits something and reflects to us. Now, if it absorbs half the colors, let's say it absorbs all this blue and green, we're going to see red. If it absorbs, let's say, the green, yellow, and red, we're going to see blue. Or if it's for some other reason, it actually reflects or fluoresces, let's say blue, we're going to see blue. So this is what's behind what we see. This, by the way, never mind this for now. The fact is that this is an equation used. The c is the speed of light is equal to the wavelength. That's how the shorter is going to be higher times the frequency. That's the speed of light is equal to the frequency here. That's the nu. That's the v-like thing. It's actually a Greek letter nu times the lambda here. That is the wavelength. That's just an equation people use to relate frequency to wavelength. In any event, we should know that our light is composed of many different colors mixed together to form white. And when some of it is reflected to us, we see that. When some of it is absorbed and we only see the rest of it, we see only that color. Okay, so we now know that white light, the clear light, that comes from a light bulb or from the sun, is composed. It's what we call white light. It is a mixture of all different colors. Sometimes light, an object absorbs certain wavelengths, and what we see is the part that are not absorbed, and that is the color we see. That is why certain things are colored. Now, this is true for not just visible light; it's true also for cosmic rays and radio waves. Sometimes things are absorbed and others are not, and we see or we can detect, because we can't see radio waves, we can detect what's left behind. The fact is, all matter, all materials, they absorb light to a certain extent. Now, you might think a brick is not absorbing anything, and you would probably be right, but if you take a tiny piece of it and you dissolve it, or a really, really tiny, very, very microscopically slim piece of that brick, light will get through it and be absorbed by it. Which technically means that when light hits a brick, the microscopic surface of the brick will absorb a little bit, but by the time it gets past that microscopic depth, nothing is being absorbed. In any event, we're going to assume that everything can absorb light to a certain extent. Now, they don't always absorb all the frequencies of light. They don't of the visible light. Sometimes they absorb only in the infrared. Sometimes they absorb only in the ultraviolet. Sometimes they absorb the blue and not the red. Sometimes they absorb the yellow and not the not the blue. Many different possibilities. The fact is that different molecules, different pieces of matter will absorb light in different ways and in different parts of the visible region of the spectrum, or even the ultraviolet or infrared region of the spectrum. They will absorb different frequencies, different wavelengths, in different ways. Some will absorb more of one than the other. So, as an example, you know that trees, they take in sunlight, white light, and their leaves are green, and that's with the chlorophyll. It absorbs the light and uses it for energy so it can grow and do whatever else it has to do. The light that trees absorb is red. It is absolutely not green. The fact is, because the trees absorb all the red, what you're seeing is what is not absorbed. What you're seeing is green. So trees like red light, not green light. They can't use green light that much. That's why leaves that absorb the light are green. They absorb the red, leaving behind the green to reflect to your eyes so you can see it. So, as we mentioned, different materials absorb different wavelengths of light in different amounts. And in so doing, we can actually differentiate between two different pieces of matter by what light they absorb. Now, here's an example, something that I've done myself. Here we have three different species of what's almost the same thing. It's flavin mononucleotide. Never mind all that. There's 3 species of something that's almost the same. If you want to know, it's FMN. There's the N5 methyl FMN. Here's dihydroquinone FMN, but they're all FMN. And you can use this what they call spectroscopy, the spectrophotometer, to differentiate between the two. This one, this is probably the most visible one. What this graph tells us is that I shone light at 700 nanometers. A nanometer is 10 to the minus 9 meters, meaning 1/1000th of a meter. Some radio waves can be about a meter, and this is 1/1000th of it. So we're talking about really very much varied. Anyway, we sent light of 700 nanometers, and then we have 600 and 500, and only this one absorbed light at, let's say, 600 or 550 or 650. This is the only one. The others absorbed nothing there, so we can differentiate this, it's called the semiquinone, from the others. We can differentiate it. And similarly, we have a lot of absorption here at 445, as it turns out. And with this, we can differentiate the ordinary FMN. This one absorbs a lot. So from this graph, we send light at 700, 650, 600, all these wavelengths of light, and we see how well it absorbs. And the device will tell how well it absorbs. And by which wavelength it absorbs at and how much it absorbs, we can differentiate between these 3 different species. So that is what they call spectrometry or spectrophotometry. So now, when we're talking about, let's say, fibers, and we want to know about the color or tiny scraps of cloth, really tiny threads, when we're dealing with things like that, or even tiny, whatever it is, tiny grains of some matter that ended up on a suspect's shirt. So we have tiny little things we've got to send. We've got to identify them, and one of them is by sending light. Just like over here. We send light of different wavelengths, and we see where it absorbs, and we'll be able to identify the object. It's the same thing, but when it's something that has to be very small, like a tiny piece of matter, a fiber, or a tiny grain, we need a microscope. So we have to send that light, all this light, all these wavelengths of light, using the microscope into that small grain or that small fiber. And from the absorption, we can tell what it is. It's not so simple. You can't always tell what it is, but often you can. And you can certainly compare 2 things to say that they're the same material if they have the same absorption spectrum. Again, not that simple, but that's the idea. We take the spectrophotometer to identify what it is, but it's got to be using a microscope because it's a tiny sample. So we use a microscope combined with a spectrophotometer to get, so we call that a microspectrophotometer. Here's a little picture of a commercial one. They're kind of expensive, but that's what has to be done. Here we have our stereoscopic microscope. It's combined to a whole bunch of things here. The light, I think, comes, the special light, gets, here's what controls a lot of it. It shoots up into the sample. The absorption is measured, I think, up here, and it goes to a computer to give you this nice little curve, which tells you it's absorbing right over here. And of course, a grain might absorb here and there, and not in one little band, but different things absorb differently. And this thing, we can see they're all absorbing at the